Thank you very much. Ohayou gozaimasu. It's great to be here. It's very exciting to give this talk because I believe we're going to be able to change the way we've spoken about quantum technology from all the talks that have come before. We've always talked about quantum technology in the future tense as something that is coming to give advantage of our expectations for this technology. But through this talk, I want to show you that quantum advantage is something available now. It is something available today, and it's through something that is a little different than many of the applications we've heard about. It's through our work in quantum-assured navigation. Now, for those of you who are not familiar with Q-CTRL, we're a company that focuses on building AI for quantum. We build new forms of AI technology that make our ability to manipulate quantum hardware better. In past iterations of this conference, I've been privileged to speak about our work with many of the leading providers of quantum computers, including our recent announcement of an integration of our software with IonQ, following what we did previously with IBM, where we build performance management software at enterprise grade. Tools that allow fully automated calibration in one click of a button. Tools that allow massive improvements in the performance of quantum algorithms with one line of code. That technology is broadly deployed, and we're very proud of the partnerships that we've built and the new research that we've enabled. So please come to a talk later showcasing how this work has been leveraged by Mitsubishi Chemical in some of their applications. But in addition, we have focused on how this idea, AI, powering quantum technology, could be applied in an adjacent vertical, something called quantum sensing. And we've pioneered the development of a new class of quantum sensors that we call software ruggedized quantum sensors, using software powered by AI to enable us to combat the degradation that comes from the outside world when we try to take quantum sensors into the real world. And we have a wide variety of partnerships across the defense landscape focused on this technology. I'll give this talk focusing on that vertical, because we're very excited that only about 3 weeks ago, we announced a breakthrough, which, as a native New Yorker, is a very proud moment to achieve the NASDAQ wall in Times Square, focused on the fact that we actually achieved quantum advantage, that we showed a quantum technology outperforming in a head-to-head contest the best classical alternative. And we did this in an emerging area of significance called navigation. Many of you may have seen this article from roughly 1 year ago in the New York Times, focused on a technology that completely rules our lives, GPS. If you came here using Uber or Lyft, if you use Google Maps, you use today GPS technology in order to navigate, in order to find your way to this location. We've always assumed it would simply be available to us, but more and more, interfering with or disrupting GPS is becoming a weapon of economic and strategic sabotage. Analyses have shown that this is an enormously high-impact economic problem, over $1 billion per day for a short-term outage of GPS. But in a strategic context, the impacts can be much more significant. This is a map of near real-time data automatically relayed by commercial aircraft flying in the sky. This is from roughly 1 week ago. You see Japan on the right, you see Europe on the left. Everywhere that you see a red marker, a large number of aircraft have automatically relayed that their GPS signal was jammed. It was blocked by a third party. And if you look closely at where you see this region of disruption, you'll note that this corresponds with all of the major flight paths between Asia and Europe, near the Black Sea, near northern Iraq, over Iran, also near the Baltic states. And so this looks like a new form of electromagnetic iron curtain that is descending over Eastern Europe and is disrupting the partnerships between East and West. Right now, since March 2024, on average 1,000 flights per day suffer GPS disruption. And this is something that causes huge concern among airline pilots. When we've spoken with pilots, over 70% rate their concern over GPS denial as very high or extreme. And they offer quotes like this: when you're clearing alarms from jamming, those few minutes require 100% of your attention. Minutes feel like hours. You have no capacity to deal with anything else. I'm very sorry for those of you who have to get on a long flight after this, especially back to Europe. This is the reality that we face today. GPS is no longer a completely reliable technology. There are backups, of course, but those backups all have shortcomings. Most of the shortcomings are that if you think about visual navigation systems, looking at the ground and identifying features, they don't work where there are no features, like over water. They don't work at night. They don't work when it's cloudy. And so there has been a huge prioritization of developing new forms of navigation called alt-nav that fill many of these gaps and work everywhere. And the way we think about this is to consider a new class of technologies that work without GPS beacons, without receiving the radio signals from satellites, and instead look more like orienteering. For those of you who are not familiar, orienteering is a game very commonly encountered in the childhood scouts, the Boy Scouts and the Girl Scouts, where you are given a map and you are asked to figure out where you are on the map by identifying landmarks. You say, there's Shinjuku Station, there is Mount Fuji, I believe I am here on the map. You use your eyes to identify landmarks and position against the map. Now, that works when you can see things, but what if it's dark? What if it's cloudy? Fortunately, there are other signatures that you can look for. And quantum sensors give us a new set of eyes to see these unseen features. These are tiny variations in Earth's gravity. Very, very small fluctuations in Earth's magnetic field. The magnetic field does not only point north, like a compass, it also has tiny bumps and wiggles that constitute a unique fingerprint for each location on the globe. And over many decades, we have built maps of this technology, of this geophysical phenomena. So we can build a new form of orienteering using quantum technology, where we start with publicly available maps of these geophysical fluctuations. We combine with sensors, the eyes that can see these fluctuations, in this case, a novel form of magnetometer built by Q-CTRL. And we combine with algorithms that allow us to stabilize the hardware in the real world and also extract a position based on the map and the signal from the sensor. This is a new technology we've built, and I want to show you what we've been able to demonstrate. I want to emphasize, though, that many of these technologies have been around and explored for decades, but they have not ever really worked. It has required innovation in quantum sensing to build devices sensitive enough, able to measure these very small signals, and stable enough over time in order to make these applications a reality. Now, we're very happy that the starting point is the fact that the maps that we wish to use are available in the locations we care about. This is Ukraine, which is a major area of concern with navigation because GPS is broadly denied. There is no data over Ukraine because there are no flights over Ukraine, no airplanes. But all around it, you see the denial regions. In addition to this kind of map, we have this kind of map. These are the magnetic fluctuations that have been previously mapped over Eastern Europe, and you see we have detailed information about the signatures over Ukraine. Now, the very difficult thing is that when we try to measure these tiny little fluctuations in Earth's magnetic field, those signatures are overwhelmed by noise, by interference from the aircraft. The aircraft is a big piece of metal flying through Earth's magnetic field. It also has instrumentation, avionics, additional sensors, all of which cause interference. And that interference as shown by the raw data from a real magnetometer in an open data set, is often 100 or 1,000 times larger than the geophysical signal that you're trying to measure. Now, this to us looked like a problem for software to fix. Something that we could overcome with the software level innovation in which we specialize at Q-Control. So we built a totally new AI-based, physics-informed, what's called denoising software technology. It's much, much better than anything that has ever come before. For instance, it is instant in its operation. You turn it on and you can begin your flight. It doesn't require recalibration, as has traditionally been a necessity in these kinds of applications. It doesn't require any in-flight maneuvers. Up until our innovation, every time you tried to do magnetic navigation, your airplane would have to take off and fly in a square for half an hour in order to calibrate the algorithm before you could continue. Imagine doing that every time you took off from Haneda. None of that is required anymore based on what we've developed. Of course, the other part is the novel sensor that I showed you a moment ago. That is an Australian 50-cent coin. It's about 2 centimeters across. This magnetometer is very small and very sensitive. For any of the experts in the room, we measure at roughly 100 femtotesla per root hertz, 1,000 times better than the other magnetometers that are widely talked about. It's quite small. It's roughly the size of your finger. And it's very, very stable. It doesn't change over time. So we began flight tests earlier this year in which we conducted roughly 27 hours of flights, fully autonomously operating this quantum navigation system in conditions that are very challenging. Things that sound simple, like turning on the autopilot, but autopilot causes a huge amount of interference. We required that in our tests. And what did we see? We saw that in real flight tests, our system, when compared against the best GPS backup, called an inertial navigation system, it's on every aircraft right now, delivered positioning now up to 100 times more accurate than the INS alone. This is the first time any quantum technology since the atomic clock has decidedly outperformed its counterpart. Here in real-world trials, where not only was it much better than the INS, but the positioning accuracy made it one of the most precise non-GPS positioning technologies. Less than 0.1% uncertainty in the position at the end of the flight, reducing uncertainty from 40 kilometers to 600 meters in this case. The best we achieved was 20 meters of positioning after a 400-kilometer flight. This is the basis of a new product that we have brought to market called Ironstone Opal, focusing on integration into commercial aviation. And we're very excited about the partnership we have built with Airbus, with whom we are working to integrate and test this technology on next-generation commercial aircraft to make all of your flights safer. But we also do focus on opportunities in defense. There is enormous growth in autonomous systems. It's estimated by 2030, there will be 2 million tactical UAVs per year produced. And we are working right now with a number of partners in the Department of Defense in the US and otherwise to integrate this kind of technology into uncrewed aerial systems. At the end of the day, this technology fixes all of the problems that we have talked about. It is available anywhere. It doesn't matter time of day or weather conditions. It is unjammable because it does not require any external signals. It is not spoofable because there is no external positioning information being sent from outside. It is passive. It doesn't send out signals like radar or LiDAR, meaning you don't give away where you are in a defense situation. And it's extremely accurate, as our world-first trials have shown. But I want to give one more thing at the conclusion of this talk. In navigation, we have spoken primarily so far about our field demonstrations in airborne platforms, the flight tests that we have undertaken. And we've addressed the big challenges that have arisen when we think about flying through GPS denial areas. But there's another domain in which there are major challenges, and that is the maritime environment. Just this week, there was a major incident with a shipping vessel in the Red Sea that suffered a GPS spoofing attack. That means it was receiving a fake GPS signal, and it navigated by that fake GPS signal and ran aground. In the marine environment, in the maritime environment, this is a major growing concern. But magnetic signatures are not very pronounced at the Earth's ocean surface. This is because the salt water interferes, there are electrical currents in seawater, and the like. There is another signature we can also measure. That signature is fluctuation in Earth's gravity. The underlying navigation technology is then called gravitational map matching. And we're excited that we're close to unveiling a new variant of ironstone opal focused on the maritime environment based on our field-trialed quantum gravimeters. This is the world's smallest 3-axis quantum gravimeter, and we're very excited that in recent tests we have shown in motion, in testing like this, that the device performs well enough to undergo navigation based on map matching in a real maritime environment. And we are commencing this next step in field trials right now. So not to be too cute, but there is a huge amount of interest in quantum assured navigation, but ironstone opal is the only quantum assured navigation system that actually works, that actually gives any form of net advantage in positioning. And we're very excited to be bringing this to market right now, and hopefully we'll be integrating into all of the different vehicles that you use to navigate the world around you. Thank you very much.